The question that we have now is, how do we locate the extrema? Extrema just stands for the possibility that we have a minimum, a maximum, or something in the multivariate realm called a saddle point. We'll learn about that here shortly. So the way we would have done this in single variable calculus is if we think about a function, let's say this one, which we can clearly see has a global maximum, and we want to locate that x value at which the maximum occurs. So here we have x versus f of x. Now the one thing that we know is that at an extremum, at a critical point, we have a slope, f prime, of that x naught will equal 0. So here's this x equals x naught. That's a value of x. And its rate of change, the curve's rate of change at that point, will be 0. So what would we do with that function? Well, first of all, we would find f prime of x and then set f prime of x equal to 0 and solve for x, right? So in other words, what we're doing here is we're finding the rate of change function, and then we're looking for the x values of our rate of change function that have a rate of change of 0. And once we've located that point, we know that we have a critical point. And then we have to determine if min or max, or potentially neither, right? It could be that, like a cubic function we've learned about, something like this, where momentarily there's a slope of 0, but it goes from increasing back to increasing. So we do what's called the second derivative test, and we determine its concavity at that point. And if the second derivative is greater than 0, we know we have a concave up function, which would be a minimum. In this case, we have a concave down function, so its second derivative would be negative. Okay, so in the multivariable realm, what we need to do is we have a critical point wherever both f sub x, the partial with respect to x, is equal to 0, and the partial with respect to y is equal to 0. Now I want to demonstrate this with a little app, so just focus on what's over here on the right-hand side. Here I have this surface, three-dimensional surface, z equals x squared plus y squared. And the value of a and b just determines where the location of that point is on the surface. So here I have this point P, and then you see this plane as well. And that plane is the plane that is tangent to the paraboloid. Okay, this is called a paraboloid. Tangent to the paraboloid at one point. So what you would see from the side, if you were thinking two-dimensional function, if you kind of imagine this to be two-dimensional function, that point right there is the point at which we calculated the derivative, and the slope of the plane in that direction is the tangent line, right? But we actually have slopes in two directions. We have the slope going up and down like this, but we also have the slope in the y direction, and we might imagine that to be the slope going horizontally, right, coming out towards us, and what would be the slope of that line? Well, in any case, if I start to move that plane around, now we know we're not at a minimum or a maximum because we see that the plane actually slopes upwards, but watch what happens as I begin decreasing the value of x. And this value x naught is just a projection of the point P onto the xy plane, so you can see what ordered pair we're actually looking at. And as I move this thing, you can see that the slope is getting steeper, which would indicate that I'm moving farther away from a critical point, right? More steep means not approaching a min or a max. But well, look what happens as I move this thing closer to 0. Do you see how that plane is starting to level out? And in fact, as I hit x equals 0, we'll notice something interesting, which is that the slope in this direction is perfectly horizontal, but the slope in this direction, okay, in the y direction, is not, right? So although I have a rate of change in the x direction of 0, I don't have a change in the y direction of 0, which means that my y value of b equals negative 0.18 is not quite right? And the further I get away from that point, the steeper it gets in either direction. But as I bring that in close to the location 0, 0, look at the tangent plane. The tangent plane is horizontal to, or is parallel to the Earth, right? And so that tells me that at that point, I have a critical point. Now, in this case, we can see it's a minimum, but how do we know it's a minimum just based on calculating a critical point? Well, so that's what we need to do. Just like in the first multivariate, univariate calculus class we took, we had to take the partial and set it equal to 0. Now we'll have to take two partials and set them both equal to 0. So to know what type of extremum it is, we use the second derivative test. It's sometimes called the d-test, to make a conclusion about the type of extremum that we've just located. So is it a relative max, relative min, or is this thing called a saddle point? Now this may look kind of daunting at first, but let's unpack it. To determine if a relative extremum of a function f occurs at a critical point, okay, so let's say we've found a critical point, and if we have multiple critical points, then we have to do this for each critical point separately. So let's just say we have one located at the point c comma d. So first, calculate the d value at that ordered pair. Okay, so this is a function evaluation, and the function that we construct for this d-test is the pure partials multiplied together minus the mixed partial squared. Okay, and so you have to compute the second partials, or the second derivatives first, and then plug in the point. You can't plug in the point and then compute the second derivative because you're always going to get 0, because the derivative of a number is, well, it's 0. The rate of change of a constant is 0. So the conditions for what do you do with this? Well, f has a relative max at that point if the d value at that point is bigger than 0 and the pure partial with respect to x, the pure second partial with respect to x, is negative. Now you think about this part, this may not make sense, what this d thing is, but if the second derivative is negative, well, that means concave down, and therefore it would make sense that we're talking about a max. If d is bigger than 0 and fxx is greater than 0, well, that means we're concave up. Well, that means we have a min. And f has what's called a saddle point at that location CD if the d value is less than 0. So if d value is bigger than 0, you have to look at the pure partial with respect to x, pure second partial. If the d value is less than 0, you know it's a saddle point. And the third possibility with the d value is that it's equal to 0, and the test is inconclusive. Just means that you have to take a look at the graph to determine what kind of critical point it is, if it's any of these. All right, well, what is a saddle point? Well, a saddle point is kind of like a combo, a mixture between a relative max and a relative min. It looks like a Pringle potato chip, or maybe like a horse's saddle. And you'll notice that in one direction, we have a minimum. So look at this direction right here. Right there, I have a minimum, right? In that direction. However, in the other direction, I'll do this in purple. In the other direction, if I travel along this way, notice that that same point is a max. It's a maximum. So I have a maximum going in one direction, a minimum going in the other direction. So it's neither a min nor is it a max relative to the entire surface, but it is a max in one direction and a min in the other. And that's what a saddle point is. We don't prefer those when we're optimizing because it doesn't really optimize our function, maybe just with respect to one variable. All right, let's run the d-test. So first thing we need to do is find any critical points of this. So let's get our first partials. That will be 2x plus 2y, derivative of 3y squared will be 0, derivative of minus 4x will be minus 4, and derivative of minus 3y will be 0. Okay, f sub y will be 0 for this first derivative, 2x for the second derivative, for the derivative of the second term, 6y minus 0 minus 3. And now what we need to do is we need to set fx equal to 0, and I'll just write set because we're setting it equal to 0. We want to know where the rate of change in the x direction is equal to 0, and then we'll set fy equal to 0 as well. Now, here, oftentimes, you have to do quite a bit of algebra. This is actually would require us to solve a system of linear equations, but using technology, we can actually solve this relatively quickly. I'm going to use Wolfram Alpha for this. There's no need to really get mixed up in the amount of algebra, but you could, in theory, if you didn't know how to solve systems of equations, solve one of the equations for one of the variables and then substitute it into the other one. So we could use reduced row echelon form to solve this in matrix form. If you did that, you'd have to move the constants over to the other side and reduce 2, 2, 4, 2, 6, -3, and do the RREF of this. Now the reason I'm not going to do that, because this is often not going to be a system of linear equations. It could be a system of nonlinear equations. So let me show you how to do this with Wolfram Alpha. So here I am in Wolfram Alpha. I already have these equations typed in. The important part here is that you enter your first equation, comma, and then your second equation that you want to solve. And Wolfram Alpha should know, if I press equals, that it's treating this as a system of equations, and it gives me the solution. Now, if there was more than one critical point, you'd see pairs here. And you'd have to run the d-test for each of them individually. Now I'm going to convert this to decimal form since these are exact. So we have a critical point at 2.25, -0.25. Okay, and according to our theorem for the d-test, the CD in this case is the ordered pair that we found, right? This is the C and the D. These are just instances of X and Y. And now what I need to do is I need to get the D function. Okay, the D function, not too bad to compute, but we do need the second derivative, all the second derivatives. Remember, with the mixed partials, we only need to compute one because they're both the same. So take the derivative of this guy with respect to x. That's pretty straightforward. It's going to be 2. Derivative of 2y minus 4 is 0. F sub y will be 0 plus 6 minus 0. And then now let's just compute fxy, which is the derivative of 2x plus 2y minus 4 with respect to y. Or you could take the derivative of 2x plus 6y minus 3 with respect to x. You get the same thing. And this is going to come out to be 2. 0, 2, 0 be the derivatives. Now in this case, what I get is the D function, the D of xy, is equal to fxx times fyy minus fxy squared. Okay, now this just turns out to be a constant. It's not always going to be the case that these are constants. These oftentimes involve x and y, but in our case it'll be 12 minus 4, which is 8. All right, so we get a function that is just a constant. So now if I evaluate D of my critical point, 2.25, -0.25, so it's like plugging that in. But note that we don't have any x's and we don't have any y's. So it's as if we have 8 plus 0x plus 0y. And I'll just write that there so it looks like, you feel like you're plugging something in, which you are. It's just they're having 0 contribution to the output. The D value in this case is just always equal to 8. Now that is bigger than 0, right? Let's see what we do when the D value is bigger than 0. Okay, if D value is bigger than 0, then you have to look at fxx. If fxx at that point is less than 0, you have a relative max. If fxx is bigger than 0, you have a relative min. So let's check this out. fxx at our point 2.25 comma negative 0.25. Well, it's always equal to 2. So again, I could write it like this. 2 plus 0 times 2.25 plus 0 times negative 0.25, just so you feel like you're plugging something in. That's equal to 2. 2 is bigger than 0. And if the d value and pure partial with respect to x is bigger than 0, we have a relative min. Relative minimum at x, y equals 2.25 comma negative 0.25. Now, if you wanted to know what the z value is, the z value at that point would be f evaluated at 2.25 negative 0.25. And whatever you get there, that would be the z value, and you could list that point as an ordered triple. And that's pretty much all there is. If you had multiple critical points, you wouldn't have to recompute this stuff at all. You would just have to come down here to your d-test and plug in your other ordered pairs. It's like I said, it's not always going to be a constant like it is